All right, last example for 6.2. By the way, before I forget, I should say 6.3 is another section about solving trig equations. So it's part 2 of this discussion. Okay, so so we will be talking about a little bit, some more techniques for solving different kinds of trig equations. And I think in that section, more so than in this section, you understand why I solve equations the way that I do. So I'll be sure when I post the lectures for that section, I'll be sure to explicitly say, why I like to solve trig equations this way, that I solve them. Okay, well, let's solve this guy. So looking at this thing, it's like, so one thing that occurs to me is so if I try to move the secant over so that I have a 0 on this side, and then I try to factor this, well, it's not going to be really possible to factor. I don't have anything quadratic going on, so it's already factored essentially. So I don't think that trick really works. I am thinking, tangent is sine over cosine, and secant is 1 over cosine. If I multiply through by cosine, then I'm going to get sine x plus root 3 cosine x equals 1. That's kind of nice, but then I still have to grapple with the fact that I've got a sine x and a cosine x. I may be opening up a can of worms for myself. So here's another trick, and this is just a trick that I know from experience from solving trig equations. Anytime you see a square root going on in your problem, you don't always have to square both sides, but it's a good thing to try if you're stumped, right? If you're stuck, you can say, well, I've got this square root, maybe I should try squaring both sides. And notice that if I square both sides now, I will have some quadratic stuff going on. I might have a better shot of, like, say, moving this over and factoring or something like that. So that's what I'm going to do. I'm going to go ahead and square both sides and see where it leads me. So squaring this, remember, so you can't distribute the square across the addition. So this isn't just going to be tangent squared plus 3. You have to actually write it out twice in FOIL. I'm going to do that in my head, right? So I would have a tangent squared. Then I would have a tangent x times root 3 and another tangent x times root 3. So that's going to make 2 root 3 tangent x's. And then I would have a root 3 times a root 3. Okay, and that makes 3. Now the good news is you can pause this, right? If you're like, what? Like, how? Pause it. Write this out twice, FOIL it, simplify. You should end up here, okay? But this is the left-hand side after we square. The right-hand side, of course, is just going to be secant squared x. Okay. Now the good news here. One of the things that we try to do when we're solving trig equations, we try to write it in terms of the same trig function. And the good news is that I can do that now. I've got a Pythagorean identity that relates secant squared to tangent squared. I could change tangent squared into secant squared as well, but then I'd still have this tangent to the first power here. So I don't think that's the thing to do. I think the thing to do is to change the secant squared into a tangent squared. Okay, so that's what I'm going to do next. Using a Pythagorean identity, I'm going to say left-hand side, you stay the same for now. But right-hand side, oh, what is this? Secant squared is tangent squared plus 1. And that's beautiful, right? Because now if I subtract the tangent squared from both sides, they just cancel. And then I can subtract the, well, do I want to do that? Actually, I don't even want to subtract the 1 over to this side because I don't need to factor anymore, right? I've just got a single trig function right there left over. So actually, I think what I'm going to do is move this 3 over there. Okay. So I end up with 2 root 3 tan x equals -2. Then I can divide by the 2 root 3. Tan x is -1 over root 3. And look at how much more simple that is than what we started with. Right? That's beautiful. That is a beautiful, beautiful thing. Well, let's see. So we can say x must be tangent inverse of -1 over root 3 plus n pi. Okay, and that's it. You can plug this into your calculator, see what you get. We should be able to do this one in our heads though, right? This is sine over cosine. So it's when sine is 1/2 and cosine is root 3 over 2. Sine is 1/2 at pi over 6, right? Since this is negative, I'm thinking negative pi over 6, right? So this thing should be negative pi over 6. One thing that you do have to be careful on, though, with these kinds of problems, when you're squaring both sides of an equation, you introduce the possibility that you have that you've introduced extraneous solutions, right? In other words, it's possible that you've ended up with some answers here that weren't actually solutions to the original equation. So what you should do is plug those back in, right, and check to make sure that it actually works, right? In this case, I mean, if negative pi over 6 works, then obviously, if negative pi over 6 works, then definitely every 2 pi units after that is also going to work. I'm not sure if every n pi units after that is going to work, so maybe we should check. Maybe we should check both of those. So for right now, I'm thinking that if I'm looking for the solutions that live between 0 and 2 pi, if I plug in 0, that's too small. If I plug in 1, I get 6 pi over 6 minus pi over 6. If I plug in 2, then I get 12 pi over 6 minus pi over 6. And if I plug in 3, then I've gone too far. So for right now, I'm thinking that that's my solution set. But maybe let's check these. Maybe let's check these to make sure. So if I plug in 5 pi over 6, tangent of 5 pi over 6 plus root 3 is 2 root 3 over 3. Okay, secant 5 pi over 6. Over 6. Sorry, used the wrong function. Hold on a sec. Cosine. Tangent 5 pi over 6 plus root 3 is 2 root 3 over 3. Secant of 5 pi over 6 is negative 2 root 3 over 3. So I think that one's not a solution. Let's try 11 pi over 6. So I'm going to say tangent of 11 pi over 6 plus root 3 is 2 root 3 over 3 again. Right? 2 root 3 over 3. Secant of 11 pi over 6. That's 1 over cosine 11 pi over 6. That's 2 root 3 over 3. So 11 pi over 6 is a solution. Okay. So this one must have been extraneous, right? This one was extraneous. We got that extraneous solution because we squared both sides of this equation. So I guess in reality, all of the solutions that live between 0 and 2 pi are going to just be 11 pi over 6. Right? So we just get one solution for that problem. One solution that lives between 0 and 2 pi. Okay. If you were trying to describe all of the solutions, then I guess, we got 5 pi over 6 when we plugged in 1. We got 11 pi over 6 when we plugged in 2. So I'm thinking that's probably the solution set for all of the solutions, right? It's just the even multiples of pi that generate the solutions that are not extraneous. Anyway, so that's that. That concludes our discussion of section 6.2. Like I said, in 6.3, we'll talk about solving some more trig equations.